Awesome. Yes, welcome back, everybody. I'm going to try not to use a collab today. And I still want to, I think I've been reading everybody's feedback, which was really helpful. People said there's lots of good things about the breakout. There's, other things we can improve, of course, but one of them is just taking a break in the middle. So I don't want to do the standard breakout every time without trying some different things, but I'm going to try to at least pause in the middle sometime and let you stretch or think or ask questions or whatever we want to do at that time. And if I go too long without doing that, tell me, remind me. Oh, you know what else? I'm going to try to be better about watching the chat. I somehow failed to see the chat until the breakouts the other days. Okay, awesome. So today we're going to do perception. The first day of many days that we'll spend thinking about the perception problem. And so, in a nutshell, so far we've done pretty simple pick and place operations, but we assumed perception oracle. I don't know, the name oracle, I guess maybe not everybody knows, but it's, an oracle is maybe a person or a device that you could ask for the ground truth answer. You could always just ask them what's the answer, and they will give it to you. And we've been assuming that someone always told us exactly where the object was, really, the object in the world frame, and that's a big assumption. So, the way we've been wiring it up when we use the full manipulation station is we use these orange labeled ports. And those are the ports that are labeled as roughly cheat ports because they're available in simulation, but they're not going to be available for the comparable system, which is the real robot API. So the goal for today is to stop using those cheat ports and start using the cameras instead. Now, computer vision is hard. We've been, that hasn't completely changed. It's gotten a lot better. In fact, the fact that deep learning has done so much for perception in the last few years is maybe one of the reasons that we're able to teach this course, because you can do so many more interesting things in manipulation with color-based cameras now than you ever could before. So a lot of computer vision is based on the idea of using the RGB, red, green, blue images that come out of a camera, just a picture you'd get from a camera. But it's too simple to say that deep learning, everything in robot perception these days is deep learning. There's been another revolution that I think is as impressive and as strong over the last few years. And it's been fueled by, for instance, augmented reality and other sort of VR applications. And that has been using depth images and geometry. And that's how I'm distinguishing in the lectures between sort of deep perception based on deep learning and really data-driven, finding correlations in data, versus geometric perception, which we're going to talk about today, which is really thinking about taking cameras that measure something about the geometry of the system, not just the color, and using the geometry to try to do some reasoning about where, for instance, the object is in the scene. So there's a bunch of different geometry sensors that have fueled robotics over the, even before cameras, we were able to use cameras as effectively as we've been using in the last couple of years. You probably have heard of some of these. You might have seen an autonomous car drive by with a Velodyne spinning on its top. It looks like a little, trash can on the top. Those are hugely capable sensors that are getting incredible views of the surrounding area. They look a bit like this. This image I've picked here is actually from the Luminar, which is one of the newer lidars. They have boast incredible range, up to 500 meters range with really pretty darn impressive resolutions. For smaller, non-car sized vehicles, if you wanted to use a LiDAR on a manipulation system, you would tend to be using something more like this Hakuyu, or if you wanted to strap it to a helicopter or something like that. These have tended to be Hakuyus, although I've seen people strap everything to a helicopter at some point. Okay, but they're based on the same basic technology of sending out a pulse of laser and measuring the returns, okay? You can also go from just a pair of images and try to learn something about geometry. There's a natural front end that you can do that just does stereo block matching or some slightly nicer versions of that, where you take the two images, you go basically subframe by subframe walk along and try to find, for instance, in each row, the closest row in the sense that they have the image looks as the same, as close as possible. And using the known distance between the cameras and the triangulation, you can extract the depth. And this one here, it's maybe not one of the most familiar ones, but it's the one we spent a lot of time with on the Atlas robot. That's the stereo head that we carried around on an Atlas from Carnegie. It was a very, very good system. Point Grey has been building stereo camera devices for years. They come up with similar looking images. People tend, want to paint these depth images with the color corresponding to the depth. And so you'll see things that look like this out of all of these kinds of sensors. But there are other kinds of sensors too. There's the Connect sensors, where that was a big deal when that came out, because it brought the cost way, way, way down. And unlike the LiDARs, which were very energy expensive and worked well outdoors, this was a camera system that could return, first of all, both depth and color in the same system, and it was well suited to indoors, but not outdoors. So this was maybe one of the first big pushes on the manipulation type geometry sensors. And it used, and many like it, we used an XGeon lab for a long, long time. It kind of, I think the model went extinct, I guess, as it would, and you couldn't get one anymore, but we just held on to that one Acteon that we had for as long as we possibly could, because we loved that sensor. The idea there is actually a super old idea, but implemented very well. You can project a pattern onto the surface and then use a single camera. This one actually uses both RGB and an IR camera in the Connect to basically infer depth from that. But the one that we are going to spend the most time with today is almost just a standard stereo camera, with one exception, which is that if you were to take a stereo camera that was just taking two images and trying to find matches and point it at a blank wall, then you'd get no returns. And so that actually happens more than you might think in an indoor environment, not just big blank walls, but any place where you've got some non-negligible, or lack of texture. So to make them a little bit more robust to that kind of thing, people put in, Intel has made a very nice series of cameras where they have a small projector built right into the camera, and they project a infrared pattern onto the surface, and that gives just a little bit of texture even when there's a textureless environment. But otherwise, it's basically doing the stereo matching algorithm that we talked that you could do with just two normal cameras. Now, compared to there's a couple of reasons that we picked this sensor. It's not perfect. In fact, when you start playing with real data from the sensor, I've got one plugged in right here. If I'd had 10 more minutes before lecture, I would have projected a point cloud of my face to you, but I didn't quite get that done. But maybe given what I'm about to say, that was probably good. But the images that come out of these things, the first word that almost everybody uses is lumpy. That looks kind of lumpy. And there's just something characteristic about this particular sensor where you take a depth return from a pretty flat surface, and you'll see kind of a wave field kind of response. And some of the objects that we care about are in that noise floor, or that sort of the noise of that wave. So we had a problem set last year where we thought, oh, we're going to build the problem set around making you pick up a spatula. And it turns out, the place we picked the camera, the spatula was about the same size as the bumps and didn't work so well. So we had to change that out. Okay, it's not perfect, but it's an amazingly good sensor. And compared to some of the other sensors, there are cameras in this form factor, even in the RealSense line, that use time of flight. But they have the problem that they can interfere with each other. So the nice thing about a projected texture is that it's not assuming that it gets a particular texture out. It's just putting something out there that gives me something to match with. So if two cameras are projecting two textures, no big deal. It doesn't assume, and so the ability to set up multiple cameras all looking at the same scene is a major advantage, and that's maybe the biggest reason why we picked this camera to focus on for the class. So we can simulate the cameras in Drake and on Colab. There was a scary moment the other day when I thought it wasn't going to work, but it's all good. So yes, so you can simulate them in Drake. The way it works is you add basically an RGB sensor object to your diagram. It plugs in, as you might expect, to the scene graph, not to the multi-body plane. The scene graph is the curator of all the geometry, and you can ask the scene graph, what in the world do I need to render? And then you put the RGB sensor model there, and out comes color images, depth images of different types if you want. One of the ground truth cheat ports would be to have a labeled image saying what is the ID of the object that is in that pixel, and so on. Now, that's an unassuming little box in a diagram, but that's got a full-on rendering engine behind that. So the one we're going to use mostly in class, we can do pretty well for our purposes with just a simpler OpenGL renderer. It's actually, we have a couple of different options, but the one we'll use is going to go through VTK, which is just a nice wrapper on a visualization toolkit that's a nice wrapper on OpenGL. But it's a shader-based rendering pipeline for anybody who's done computer graphics. There are alternatives as we've increasingly tried to improve the fidelity of our simulator to match reality. You can put in a full-on physics-based rendering engine here, things that you, for instance, would do ray tracing, and we can connect it to Blender, for instance, and try to get very high-end images. We tend to do that when we're generating training data for machine learning pipelines, but we tend to not do it in our closed loop simulation tests just because it's very expensive. But the future is going to just make those better and better. So the outcome of that RGBD sensor is both a color image, like I said, and a depth image. And I'll show you, I've picked one of the standard you see in manipulation. There was a data set that was released a while ago called the YCB objects, and they had a handful of, this was Yale, Carnegie, and Berkeley authors from each of these places. They did quite a service to the community by not only scanning objects and putting high quality texture maps on them, but they also made them available. So you could say, hey, co-author, could you please send me the items on this list? Or they could give you like the Amazon part numbers on that list. And so it was a good way for many people to start picking up the same non-trivial objects. But as a result, you'll see everybody who's talking about manipulation has like a French's mustard bottle or a Cheez-It box or a Spam can. That's one of the really weird ones you'll see. C'est la vie. Okay, so here is a first thing to do. I hope that's loading, yeah. Do I not have a? My rendering's not there. Is anybody else seeing it? I'm not seeing it. Is my computer just slow, or did I forget to add that slide? Let me think if I can get the right URL. Yeah, give me 1 second. It's worth getting that.
Oh, there it is.
Yeah, it just took forever. But that's because the YCB objects are not small files. That's one thing that they did do a huge service to the community, but they are also they're big old texture. Like the image that is the texture map of the French's mustard is like a 9 megabyte file. So use them, but feel the pain. Okay, so here's just a standard MeshCat scene. I've inserted a camera. modeled as a gray rectangle with its camera frame here. So the camera is always looking at vertical Z, and the XY images of the XY coordinates of the image follow the XY axis. You know, remember our red, green, blue axes here. Okay, and this is now a deceptively important sort of render of the mustard bottle, because if you open your controls up and disable the ground truth label that the world gave me, then you can see I'm rendering both the point cloud as well as the actual sort of ground truth mustard bottle. Okay, and you know, there's something that happens when you do that, which is, I don't know, for me, until I started doing that, it's hard to think about the limitations of a camera, right? So you get in this case, we assume a perfect depth returns basically, but and perfect, you know, coloration, but you still, even in the perfect case, you only get to see part of the object, right? And in fact, that's a major concern for a lot of these systems is what can we do if with only partial views of the object? You can imagine if there's multiple objects in the scene, then occlusions are going to be also a big deal. And probably if it's sitting on a table, you'll actually never see the bottom of the mustard bottle, right? So if you're writing algorithms that are expecting to match points, for instance, all over the object, you are going to fall down and fail when you have real sensors, even simulated sensors.
There's a question on the chat, Russ.
Nice. What is the approximate Z resolution of the D415? I bet Zooey knows. Do you know, Zooey? It's millimeters, right? But
sorry, what's the question again?
What's the Z resolution of the D415?
I know it's ranging from somewhere 0.3 to maybe 1.5 meters.
Sorry, say millimeters, yes?
I think it's millimeters, yeah.
Yeah, 0.3 to 1.5 millimeters is what you have in your memory.
0.3 meters to 1.5 meters, but the resolution.
That's the range, yes.
That's the range. And each numbers, I think it's millimeters, yeah.
So, but at halfway, like somewhere in the middle of the range, how accurate is it? Like how many millimeters are the depth estimates accurate to?
So it outputs an 8 bit per pixel. So, and it's in millimeter range. So normally we convert it back to millimeter by divide by 1000.
Mm-hmm.
Yep. So I guess it's within millimeter range. It's the accuracy.
Yeah. Cool. So yeah, they're pretty good apart from the lumps. So they're right, accurate, not precise, something like this, but precise, not accurate, maybe. So good. Now, because of this limitation, there's a couple ways you can get around that. You can, first of all, move your camera around. So sometimes we will mount a camera right to the robot's wrist, for instance. But there's a problem with that too. Like actually, Zooey just pointed out, the minimum range is about 0.3 meters. So once you get pretty close to the object, like for instance, when you're about to pick it up, you're probably inside the minimum depth of the object. So you actually go blind with your perception sensors if you've got them mounted on your wrist, which is right when you want them to be good. So that's kind of annoying. Or you can mount multiple cameras around the environment, the scene, and that's what we tend to do for now. It doesn't work if you're going to start making a mobile robot that has to go, drive around and go into new locations. But if you're going to have a robot operating in the same environment for a while, cameras are actually pretty cheap. So we tend to stack them up. This is actually, I grabbed one of the frames. Thank you to Eric for this, from the dish loading example that I gave you, I showed you on the first lecture, the robot loading the dishes from TRI. And you can see our little D415 sprinkled through the scene there. There's actually one hidden in the cabinet there looking, so you can see in the dishwasher. There's a bunch looking down here because, my gosh, if you think about why, the looking into the sink, there's so much clutter in the sink. And then the robot's hand is going to come in and block most of those cameras. So anything we can do to try to look into that sync is worthwhile. And then there's actually 2 on the wrist, 1 on each side. This is borderline excessive, but it's, the conservative, if we don't want to, slow ourselves down, because it's silly to slow yourselves down by not putting one more camera on. Okay, but the simulated world I just showed you is actually way too good to be true. We're going to enjoy the perfection of it the techniques we're going to use today. But we're going to also think about what happens when the point clouds are more noisy and they have outliers, and dropouts is another thing. So this is just with this camera, yeah, I think this was with this camera, a standard scene in the lab. This is the depth image if it was perfect, and this is the real depth image. So those blacks are actually just no returns. So a lot of times around sharp edges or reflective materials, if there's a mirror or something in the scene, or even just a saran wrap on your object, you can just get no return there, and so you get gaps in your depth image. Okay, and these are real, and they can dominate the performance of the algorithm. Good. So are there depth cameras designed for very small objects? There are not as many as you might think. I think that's starting to change. I mean, you can get a depth camera in, I guess I got a depth camera in my newest iPhone, right? And we're getting better and better there, but miniaturization has tended to not be their focus. In fact, even when we've talked to manufacturers about it, it's been like, oh, you're the first person who's asking us to see closer or smaller, whereas they tend to get requests to try to see farther and farther and higher power and stuff like that. Yeah, min-z as small as possible is a requirement that I've been surprised at how few the people emphasize that. Yeah, picoflex is good, yes, for instance. It's not just from reprojecting between RGB and D, are the gaps there. You can actually, it depends on which type of sensor you're using, but many of them will fail to match, or will think that the best matches that they can get is in the farthest. I mean, it's easiest to think about if you're sending a laser pulse out or something, and it glances off the side of an object and just doesn't come back, for instance, or if it's reflective, it could go off in some different direction. But even in the stereo, I think you can fail to match and get these kind of artifacts. This is great. You can also feel free to speak too. That's good. Okay, so yes.
Sorry, there's a question about like LiDAR. I mean, people have stuck the LiDAR on like newest version of iPhones these days, or iPad. So people are kind of wondering, why not use LiDARs instead of cameras?
Good. So we're going to care. So some of the geometry sensors like LiDARs that are time of flight are only depth and not RGB. But the one, sorry, I wouldn't call, is this a LiDAR? This is maybe a time of flight. I don't actually know exactly what the sensor they put in here is. But we definitely want both. And we tend to, LiDARs tend to be, the ones I think of as LiDARs, the big Velodynes and the like, tend to be for higher power requirements. For instance, if you're fighting against natural light of the sun, then you end up with a big laser-based solution. And some of the, more stereo solutions are better are adequate indoors and much cheaper. Cool. Okay, so let me switch to writing. Okay, so it turns out there's a couple reasons why I wanted to do geometric perception before deep perception. In my mind, it's actually it's a little more satisfying. We can use the mathematics of our geometry. We can understand when things work, when they don't work, and there's a huge class of problems that they really do address nicely. But my secondary motivation is it dovetails perfectly with the kinematics stuff we did just in the last couple lectures. So let's start thinking about perception as actually just a problem in kinematics or inverse kinematics, if you will. Okay, so let's say I have my object O, and since I'm in 2D on my whiteboard here, I'm going to just draw it as some non-symmetric for simplicity object. And we've got a couple different ways to represent the geometry. I could represent it as a mesh. I could represent it with its line segments, I guess, in the 2D case. But as you can see, the images that we get back are pixelated, of course. They're a depth image. And the rendering I showed you of the mustard bottle was actually a projection of that depth image into the 3D space, which I'll talk about in a second. But it's a point cloud, we call it. Okay, so so it's natural actually to represent even our objects for the beginning of this discussion as just a set of points. Okay. So let's say that we have an object model. Okay. Let me get my colors right. So an object model might be if I have some object frame, right? This is my object's X direction, object's Y direction for the object frame O. Okay, then my model might be the location of all the points relative in the object frame, for instance, right? So I'll call it the model point I in the object frame. And again, there's many different representations of geometry we'll use throughout the course, but a list of points is actually a pretty reasonable one for today. Now, I get something different from my camera, right? So from my depth camera, first I get a depth image. Okay, but if I know where the camera, well, let's see, even before I know what the camera is, if I know the intrinsics of the camera, meaning the projection that is described by the optics of the lens, for instance, that tells me how to project a point in my image into a space, I've got into a place in 3D space. So that'll give me a bunch of points. Let me call them the scene points relative to the camera. So this is my object frame. This is my camera frame. And these are my scene points, I'll call them, my observations. Let's assume for a minute that we know, well, for a while, maybe, for today, the location of the pose of the camera in the world. Now, if camera is mounted to the wrist, then that was just a forward kinematics computation, which we talked about last time. If it's mounted on the wall, it could just be a constant. Okay. So the goal of perception for today is to estimate the pose of the object. Of course, the goal for perception overall is much broader than that. You might have to understand what's in the scene, try to decide if, the food's burning, whatever. There's like a ton of things you could ask for from a perception system. Estimating the position and orientation of a red brick is just the starter example. Okay, so I feel like there's a couple things we can understand in this very simple setting that are going to pay you dividends later if you understand them well. So I actually want to spend a little bit more time today on some of the math that is involved in understanding these transformations and this inverse problem, if we will. Okay, so the way to think about it, I think the simplest way to start is to make a big assumption that we will soon remove. But let's start by assuming that the model points and the scene points are the same in their relative frames. Okay, so that if I take my object over here, apply some rigid transform to it to put it in some other frame, right? I've rotated it and translated it, but the points that I'm getting to think about are the same points, just rotated and translated. Now you can imagine that's not what really happens, because if I actually have a camera, it's gonna, I'm gonna get whatever points I happen to line up with my pixels on my camera. Both cases, I'm gonna get a discretization of the real system, but I'll get a different discretization depending on the location of the camera. And that problem gets harder. But it's simpler to think about the case first where those are the same points. And even more, what I'm saying is that I actually know which point corresponds with which other point. So I'm going to say that the ith point is actually the ith scene point corresponds to the ith model point. So somebody has gone through the returned image and labeled basically which pixel is which. Okay, so perfect known correspondences. Huge assumption, terrible assumption, only useful to get us started. And some people might argue that the correspondence problem is sort of the essence of computer vision. So I feel a little bad pushing it aside, but this is the way we go. Okay, so if that's the case, then you can see, I mean, not surprisingly, but this is just a kinematics problem, right? So if I wanted to write my model points, let's say in the world coordinate, I could write them two ways, right? I could write them, well, first of all, from my object and my object model. But I could also, if those are the same, write them from my camera coordinates, right? And my camera model, my camera sensors returns. So in this case, this is known. We assumed that these were both known. And this we have to estimate. These equations that I wrote, of course, are just forward kinematics, right? This is just the one link version of forward kinematics. Pushing things from the relative frame to the world frame. And so we could we could try to find a solution. So the way I've written it here, this is actually even a set of equations that is linear in the pose, depending on exactly what representation we choose. Let's actually be a little bit more specific. So let's choose rotation 3x3 rotation matrices. Ooh, that went badly. In that case, for the 3x3 matrices, this thing is just the position of the object in the world plus the rotation matrix of that object in the world, 3 by 3 times PO MI. So if both of these are unknown, and this is known, it's still looking good because, like we said before, we really like linear algebra, basically. That if I can try to, if I want to solve a system of equations where the unknown parameters are linear, that's a good place to be. But if I think about the system of equations that I've gotten here, right? So I actually have a different equation for every scene point I, right? So I have P0 plus R0 for all I, okay? So if I think about how many equations and how many constraints I have, in most cases, I'm going to be over-determined, right? I'll have more constraints because I have typically more sample points than the number of decision variables. So I've got a lot of linear equations. And I guess in the case of perfect simulated pixels that were just translated, then you could actually ask for equality. But if there's any noise or anything, that would be a very fragile operation, I think. So you won't be surprised to think that to know that I think it's better to write this as a optimization, a least squares optimization. Right? I see this as AX approximately equals B, just like we did last time. Okay. Okay, so estimating, so now in this case though, it's a little funny because even though R is our matrix here, right? The unknowns X are my P0 and R0, right? And my data matrices A and B are these other things. They're built up from, this is A, I guess, and this is B. It's not all of A, but it goes into A. Yeah, there's also ones. Okay, so this is an inverse kinematics problem. So I think the question you should ask, you're probably thinking yourself, is didn't I just go through last lecture saying, let's not do inverse kinematics, that's a hard nonlinear optimization. It's way better to do differential kinematics, right? Just use Jacobians. So why am I changing my tune now? What would the differential kinematics do here? What do you think? Good, because the objects aren't moving. In some sense, I'd actually like the differential kinematics better if they were moving, but that you're on the right track. The differential kinematics, you're exactly right, are going to tell me what a small change in my pose will do to a small change, for instance, in the location of my points, which is super useful to know. So actually, we should think about differential inverse kinematics. For instance, tracking would make good sense. Once we have an initial estimate of the object geometry, the object pose, we want to understand how it changes incrementally. Awesome. That's a good place for it. But we don't actually have that luxury yet. The perception problem puts us in a place where, so basically I would do differential kinematics if I could, but the situation is a little different. So for the robot, we can measure Q and we know our current state, and we get to think about what changes to that state are. In the perception problem, we don't actually have that initial guess to start. So when the robot wakes up and the cameras turn on, yeah, even if the object is assumed to be static, yeah, but or not. So, but in that initial wake up, the robot wakes up. There's an object in front of me. What's the initial guess that I have to somehow change my kinematics from some state and to ask about how it changes, and I don't have that initial. So at least once. We have to solve the harder problem. And in practice, you might need to solve it more than once, because even if you're just tracking objects, for instance, and you're looking at incremental changes in the point clouds, it's very easy to lose track. Maybe if it goes behind and occludes and comes back. So there's often cases where you can't assume that you have only incremental problems to solve in the perception side. Okay, so what does that inverse kinematics problem look like? I guess I've written it there, but I think it's going to be much better because it's over constrained to write it as an optimization problem. So what I'd like to find instead is minimize over P object and R object my total sort of perception error, which would be, if I write it out like this, using my rotation matrices, minus my P world C9. I'll go ahead and use the world projection. That's just a constant, okay? Something like this. Now, I'm going to sum over all of the points in my scene, which is a little bit different than what we did before. And I'd like to find somehow the least squares estimate to all those constraints, which again, this looks just like AX approximately equal B. But there's a wrinkle. What's the wrinkle? If I were to just solve this for P and R0, where P is 3 by 1, for instance, and this is another 9 numbers, then the thing that I get out won't necessarily be a rotation matrix. So it can't be understood as a pose. Okay. So really, in order to make this a problem that's going to do proper inverse kinematics, I need to add new constraints that say somehow that it's a rotation matrix. Okay. And so a good way to write that is to say R transpose equals R inverse. That captures almost everything you want. But you could still get a roto-rotation, they call it, or a reflective rotation. So you actually also need that the determinant of R equals +1. Good, so why is the inverse kinematic problem more difficult? It's because of this constraint. You predicted what I was going to say here. So these constraints make that problem more difficult. If we could just solve the AX equals B, it would be great, but we cannot because of those extra constraints. Now, just a refresher on linear algebra. So, I mean, you could, let's think about what these things mean. So actually just having this property implies that the determinant of R is either plus or minus 1. Okay, but you could get a roto rotation. So there's really an additional constraint saying that's got to be the +1, the one that doesn't have any mirroring. Now, okay, so that's a linear, well, it's a quadratic objective because it's trying to solve an approximate, at least squares solution to a linear system of equations. So you should think of that as a nice, beautiful bowl. If I really want to make that rendering, I didn't think I could, and I realized just before lecture, like, there's a way I could do that. So I'm going to make an image tonight. But yeah, so think of this as a bowl, but it's in high dimensions the way I've written it. That's why I didn't think there was a nice way to do it. But if I have to plot over 12 dimensions, then it still looks like a bowl, but it's a little harder to render in 3D. Okay. But then what does this constraint look like? This determinant, this R transpose equals R inverse. That's, I mean, another way to think about that same constraint would be if you write it as R transpose equals I, the identity matrix, right? So really, this is just a bunch of quadratic constraints. Some of them saying like R11 squared has to equal 1, for, things like this. It's a bunch of, it's not quite that simple. It's whatever I get for multiplying these things out. Equals 1, some of them have to equal 0, but that's quadratic constraints. And it's a quadratic equality constraint. It's a particularly good one in the sense it's got special structure, but the general class of quadratic equality constraints is not one that we would often expect good solutions for. Let me be more careful. This one is a quadratic equality constraint. This one here is even worse. It ends up, I mean, if you remember your determinant, you pick this one, determinant of 3 by 3 matrices, and then you take it, it's this scalar times the determinant of this, times this scalar times the determinant of the other ones. There's, good old determinants of 3 by 3 matrices. But if you think about that, the top corner times the determinant of the middle, the determinant of a 2 by 2 matrix is quadratic times another scalar. So this is actually going to be, at least, it is going to be cubic. It's not a great thing to optimize over. So we get almost there if we ignore it, and it's the worst constraint of the bunch. So we're going to go ahead and ignore that constraint. It's called a relaxation. This is not an irresponsible thing to do. This is it's got a technical name. It's an enlightened thing to do, is to find a relaxation for the problem. You can understand it in the that removing constraints, has a place that we can understand in the optimization hierarchy. For instance, one of the things you can do is you can solve the problem without that constraint and then just check if that constraint was satisfied. Since we expect to just get determinant 1 or -1. In fact, our algorithms will have a case at the end where we say, solve the optimization problem, check the determinant. If it was bad, we have to do a little repair, okay? Now, I thought about going into the actual derivation, but instead I've got to cite it for you because it's beautiful and good. So this is just a bunch of quadratic equations. You can basically take the gradient of this optimization. The reason I didn't want to get into it is because it requires Lagrange multipliers, but there's a solution, or derivation, I'll call it, via Lagrange multipliers, which is cited in the notes. And it's not special in most regards, in the sense that in the way that you go through the steps. But what's amazingly special is that when you write down the constraints that emerge from your constrained optimization gradients, you get something that you realize is exactly the same solution you would get if you called SVD on the data matrix. So in practice, solution from SVD, singular value decomposition. Okay, so this is where I want to give you guys a breather for a second, but let me put up at least the 2D case so that give you something to think about while you're thinking. So let's think about the 2D example. So I parameterize my 2x2 rotation matrix. Well, first of all, the way I would normally write them, I think of a 2x2 rotation matrix in this form, right? People have seen that. But I'm not going to parameterize it that way because I don't want to use theta. Those cosines, if I wanted to search over theta, that would be a nonlinear optimization. So what I'm going to instead do, what I did in the 3x3 case was something like this, where I'm writing an entry, and then I added constraints that basically said the determinant for the R transpose constraint. In this case, turns out to be exactly what you'd expect, but let me write it one more thing first where it's even easier. It turns out in the 2D case, rotations are, it's easier to parameterize a linear parameterization of rotation matrices. If I have my first vector here, A, C, for instance, then the right-hand rule, it's always going to be a 90-degree rotation away from this. So I know that I can fully parameterize the 2x2 rotation matrices if I just do A, B, negative B, A. And that's because if I were to do R 2x2 for theta is pi over 2, then I get what? 0, negative 1, 1, 0. So multiplying this is just a simple, there's a simple parameterization of the 2x2 matrices that just uses two parameters, A and B, okay? If you write down R transpose R equals the identity, now 2x2, then you get out something that's pretty satisfying. You get A squared plus B squared equals 1. And AB minus BA equals 0. These are throwaway constraints. Okay, I was hoping to get a little farther before we stretch, but I think I'm pushing time. So I'd actually ask you maybe to think about there's a couple interesting questions you could think about right here. But for instance, yeah, you could think about the difference between this version and this, this version and this version. What does the R transpose R constraint look like there? It's actually pretty good. And another reasonable thing to check for yourself, what am I missing in terms of my determinant constraint? But take a 5-minute break. I promise I won't introduce new topics in the next 5 minutes, but I'll stand here if anybody has questions.
There was a question on the chat.
Okay. Good. So you can also pose it in quaternions. I think okay, more people do it in rotations, but I think that's because quaternions make your head spin. I think most people who implement the best versions of it often use quaternions. But it doesn't resolve because then you have to carry around the unit vector constraint. So you still have a constraint that is of the same form of like this living on the unit circle type constraint. And the solutions they follow naturally. It's kind of, it's one of the beauties of geometry that basically the same relaxations have the same effects in the quaternion space. Here's a good one. How many points do you need to give a unique solution, even in 2D? I had a bank of good questions, but I didn't quite get down to them. So. No, it's good. So that it sort of is the answer to the question, is that if I parameterize it with my A and B, negative B, negative A, or negative BA, then the determinant equals one constraint follows automatically, right? It's because I've got a clever parameterization. The thing that would happen, I'll say this again in a minute, but the thing that would happen if I got it wrong, my determinant was -1, is I get that vector out. And by parameterizing it away, that doesn't happen. So you're exactly right. So in this case, don't determinant equals R equals 1 for free. In this case, I have to be careful. There's not a direct extension of the clever parameterization. So you would like to think, oh, I could do 3 numbers or whatever, but that gets back exactly to the complexity of rotations in 3D. But no, it's everything's better in 2D. In 2D, you can just write down this nice parameterization of the rotation matrices.
I mean, even in 2D, we're over parameterizing it with 2 numbers as it is. So it's just, I wonder now if there actually could be something. I mean, you would know better than me, but by going to 4 numbers, do you get a nice parameterization out that you can do this sort of stuff with?
I mean, the quaternions are that, I think.
Yeah.
That is, yeah.
I mean, if you have A, you actually already have B if you normalize things. What is the other parameter that you normalize? It's kind of like a quaternion-esque thought maybe in 2D.
Oh, you're exactly right. So I mean, if you think about 2 equations or 2 variables, and then you have the data equations, but you have a constraint which drops your one constraint drops my number of degrees of freedom by 1 again. So that A squared plus B squared equals 1 means that if I know A, I know B. Yeah.
Although actually you're out the negative, you could still be off by a negative, which is where the determinant comes in.
It's a little more subtle in the quadratic constraint case. But in terms of the measure or something, it's like that. Okay, I have to figure out how to do that better. I don't really know exactly when I started, and I don't know if it's been useful. But okay, what's the answer to this last one? How many points do you think you need to give a unique solution in 2D? Got my object, got a point. that's not enough. I could clearly rotate around that. So I've got another point. Can you fit that shape? I mean, the shape is sort of a misleading, but if I have a line segment, how many can I fit it uniquely in this case? I think you can. It totally, it's almost a trick because everybody thinks you should require one more. But the fact that we have unique labels, we have the correspondences given, actually means you only need 2 points. And that locks it in 2D, right? I'll leave it as an exercise for you about how many you need in 3D. But you can imagine, I mean, there's no other pose you could imagine putting that in that satisfies both of those. So those correspondences give you something new. Here's a similar question. So what happens if you have rotational symmetry? If I have a box, for instance, like this, and I have a bunch of points like this. Now, I don't know exactly what your, what your brain gravitates to. Mine immediately goes to try to ask, how would the solution of this optimization over R possibly accommodate a solution that would have a good answer at 0 degrees, a good answer at 90 degrees, a good answer at 180 degrees? Like, how could that optimization stretch like that? It shouldn't. I mean, it's a quadratic bowl with another quadratic equality constraint. I don't see how it could do that. And I think the answer is it can't do that. And again, it's because you would think that it might get the answer wrong by 90 degrees, but no, because the correspondences are given. So there is no rotational symmetry when the correspondences are given. The only case, yeah?
The thing that was throwing me off about the previous question is reflections.
Yes. So that's,
if you mirror the image across the black and red point, the correspondences still match, but you have a different alignment. But that's because it's a different space of transforms that I've just introduced.
Well, that's the determinant -1 case, which we're trying to avoid.
Would it be like if it's just R plus? Well, I guess we're just doing rotations. Yeah. Okay. Yeah.
So.
Yeah.
So.
-1 gives you a reflection. So.
Trick question. All right, so what have we got now? The summary, which I hope we can get and you feel good about here. So if I give you a bunch of model points in the object frame, if I give you scene points in the camera frame, for instance, and I give you the camera frame, and if I make a big assumption that mi equals si, then I can solve for this optimization. I'll write the shorter form of it. Via SVD, which is sort of almost as good as a closed form solution, right? We can solve that to arbitrary scale, arbitrary precision with good numerical algorithms. That's just a call in NumPy or whatever that will give you that answer robustly. Now, it's not actually clear that that's the right objective. And we'll talk about that a lot more next time, but we'll talk about that a little bit in a minute here. But just like finding the least squares solution for the Jacobian version of problem, that's reasonable, it's close, but that might not actually be the best solution. So just as a simple example, what if I just don't want to return a solution that says that my red block is halfway into the table? Right? That's like a reasonable constraint to say, it's not penetrating the table. So search for the rotation matrices that don't involve putting any points in the table, right? But that would be an additional constraint on top of that. Even the objective, I think we could have objections to. Okay, so how about, but I really, really, really want to get rid of this. This is the one that we just don't have that in the real world, and we have to get around it. Okay, so if I don't know those a priori, then I've got to come up with some method. I mean, if you wanted to solve jointly for the correspondences as well as the rotation matrices, we have algorithms that will do that, but they're very expensive, often intractable. We'll talk about some of the better ones on Tuesday, but there are some heuristics that work surprisingly well. So first, let me get a notation. Let me call the correspondence matrix, or vector actually, correspondence vector in this case, Ci equals J, okay? To say that the S, let's say that means point Si corresponds to Mj, okay? And that need not, that means that these are always integers. It's an integer vector, okay? Integer valued vector. It need not be a one-to-one mapping. You could potentially have multiple scene points that go to the same model point, or multiple model points that go to the same scene point. We haven't written that as a constraint yet, and we will proceed without writing that as a constraint. It'd be a reasonable constraint to write, but we're going to be more robust in the end because we don't have exactly the same transformation by not writing that. Okay, so that would update my objective above. I would use PMCI as my sort of notation. So I would write everything I wrote before, okay, using that notation. Now, if I have an initial guess, and I talked about why I don't really have that case, but let's just say for a second, if I have an initial guess, even a bad one, for XO, then there's a very reasonable way to assign the correspondences, right? You could just use the closest point. Right, so if I have my model vector, my two objects, two possible rotation matrices, and I want to compare points, you could imagine having points on both of them and saying that the correspondence is just the closest point. So I'll correspond this with this, for instance, this with this. You can see, even in this little example, that I'm going to get a lot of correspondences wrong, okay, with that kind of a strategy. But as the rotation matrix gets more and more accurate, I would expect that to start being good, right? And in the limit where it's correct, then it'll give me exactly the right correspondences. So the interesting idea is I don't have to get the correspondences right. I just need to do, I just need to get correspondences that will make my estimate better on the next step. Call my estimate x hat of O, okay? So even if I start with an initial guess that's just hugely off, I'm like way off, okay? And I start corresponding like all of the points to this edge, that's a really bad assignment. But if I were to solve the optimization problem with that, it will still, on the next step, drag my solution over to here, and probably even in a way that maybe is more like this picture I drew as my first example. Because in order for all of these points to be close to this edge, it's going to put some on the right, some on the left. And that's enough that on the next step, it could do better, significantly better at the correspondences. So this is one of the most famous and important algorithms in geometric perception, which is the iterative closest point algorithm. And we can do better than it now, but we still use this. This is a workhorse, okay? So given an initial guess, x0 hat. Step 1 is estimate correspondences from closest points. I can write that down mathematically, but I think it's fine to do it like this. Now you can, well, let me just write it down because it's important to see it in that light. So CI is argmin. It's the J that minimizes the function of the distance here for each J, XO, POM, CI, sorry, MJ of minus PSI. So this is now what's known and unknown, right? The only thing that's unknown is J. Everything else is known. So this is not a nice optimization the way we looked at before. It's not quadratic in J or anything like this, but it's over a finite set, J. So I can solve this problem by just trying all J's. And find the optimal solution of that on each step. Now in practice, this is a closest point problem, so we don't do that. We do much more efficient nearest neighbor algorithms to do it, right? And once I compute the closest points, then I update my x hat using CI and my SVD. Wash, rinse, and repeat, okay? And that's an amazingly good algorithm to start. It has strong limitations, okay? The limitations, of course, are that it can get stuck in lots of local minima. If it starts corresponding with the bad points, it can get stuck in a local minima. Even in cases where it would be possible to achieve zero error, you can still get stuck. Okay, so it's a local method in that sense. It's also very susceptible to outliers, and we're going to talk about some ways to make these more global and more outliers robust on Tuesday. But let me switch back to show you how these things are used. almost always, if you're working with point clouds, you're going to see a bunny. You're going to see that bunny, the Stanford bunny. Okay, classic geometry. Okay, and run it one more time. This is the algorithm running. You see each iteration of the algorithm, it does a better and better estimate of the pose, leading to a better and better estimate of the correspondences. And ultimately, in this case, it appears to converge nicely to the true optimal solution. Okay, that is, there are plenty of videos we could show that don't do that, but that's the good case when it's working well. Now, watch closely in this video. This is the wrist-mounted camera of the robot picking up dishes. Okay, it's kind of stomach churning to watch it. But if you watch what's happening as it picks things up, okay, right now, you see that little adjustment there? Every time it goes to pick the dishes up, it's actually using the sensors on the wrist, the point clouds of the known object, to refine its pose estimate to go into alignment and then grab. And the more you watch this, you'll see that it does that before it picks up any sort of known object. So this gets used a lot in practice, the ICP basic pipeline. It also, even if it's feels like a crusty old geometry algorithm, you can use it in a deep learning pipeline. Maybe not online, but we often use it offline as a way to, for instance, provide data labels for a supervised learning approach. So if you have big noisy point clouds and you want to label them with ground, from real data, in simulation you can spit out ground truth labels. But this was a project called Label Fusion, which said we're gonna make a little GUI of a user interface that allows the human to just click a few times in the image, enough to give an initial guess of the pose, and then we run ICP to snap that model into alignment. And then we can go back and label all of the images with the ground truth label from that noisy point cloud. Okay, so this becomes, it's really an algorithm that still gets used today. Cool. So that was our warm up into geometric perception. I'm super keen on making that I think in 2D, I can write the optimization in rotations only using that two parameter parameterization of the rotation matrix. And I will show you what that optimization landscape looks like and what the quadratic constraint looks like on that, and see what happens when it goes degenerate and stuff like this. But that didn't occur to me in time. So I will have to do that tonight and send it out. And we're going to do, like I said, we're going to do more and more robust versions of this on Tuesday. So this was different. I want to make sure we do math when it's appropriate and visualizations and code when it's appropriate. It'll take some time to find the right balances, but please give me any feedback. And I also want to the lecture notes for this time in the course in the text are not as done as I would like, and they will be finished in the next day or two. Any more questions?
Alex, it seems like you're talking and you're muted or something. No. No, we can't hear you for some reason.
That's the okay, good. I didn't give you the full algorithm there, but it is in the notes. That was already in the notes, and yeah, you have to pull out the center of mass of the points roughly, and that gives you this data matrix in terms of the center of mass, and then it's really just SVD. It's like 2 lines. That one is in the notes and will be is easy to understand. Well, sorry, it's easy to type in, but the derivation of it feels a little magical.
Hey, Russ, I have a question on there's like another edition of another layer of assumption that the set of SI and MI, there actually exists like true correspondences. We just don't know the order, but so I guess in the real settings, this is not true because of two reasons. First one being like pixel accuracy, and second is the case where the correspondence truly doesn't exist because of like viewpoints and stuff.
So good. So there's the worst case is outliers, where you get a point in your scene that really shouldn't correspond to anything in your model. In that case, an outlier can actually pull your ICP algorithm pretty far away, like a small, one outlier that says, oops, I got a return from the background that should have been on the object, could sort of pull my whole estimate towards the background. And those are painful and need to be addressed. And there's ransack is one approach to addressing it, and then there's more global optimization approaches to addressing it. The other one, though, of the partial view, like the mustard bottle, right? The fact that I have, so that's why we write the correspondence from all scene points to the model points. And it need not be that, so you'd like to have all the scene points, and the way I wrote it today, you'd like to have all the scene points be able to find a model point to latch onto. But the model points do not all need to have a scene point to latch onto. And that's because the partial views are the dominant effect in the robotics. You'll see in the point correspondence literature, people will write them either way. But I think in robotics context, it almost always makes sense. You'd expect scene to match model, but not model to match everything in the scene.
I have a question.
Yeah.
Instead of having a known model of your object, is it commonly used to maybe, I don't know, get a point cloud from like the first time you see the object and kind of snap to that and track over time? I know it won't give you an absolute pose, but at least for relative pose.
Oh, no, totally. Yeah. So, and that is one of the nice things about representing your object as points, is that you can do precisely that. You can imagine, for instance, the correspondence point. If you did point to plane correspondence, you could potentially do better than like using the vertices of a mesh. You can do point to plane versions of this. But because you could acquire these models just from a previous scan, that's one of the reasons why you could use point to point. Also, it made the math easier today. So yes, you can. It's very hard to get a full. You have to probably pick up the object and flip it around if you want to be able to see it on all sides, even the bottom, in order to get a complete model.
Great, thank you.
No, it's good.
The YouTube people want you to show the RealSense camera again? I don't know.
What's amazing about this setup, the camera is pretty amazing, I gotta say. But the USB cable, my God, it's very hard to find a USB cable that actually powers this camera successfully. So, it has to be USB data capable or whatever. That was a little bit of an exercise to refine the right cable today. But yeah, no, it's good. It's about the size of my webcam camera. I will give you guys real data soon. I didn't have any French's mustard in my fridge today, but I had like fertilizer that looked kind of similar. So I'll find something good this game.
Sorry, just wanted to ask one more question. Why do we, could you explain your logic for all this ICP problem is necessary because we're trying to estimate the pose, right? But could we have skipped that layer entirely and just done manipulation based on points?
Good. I think yes. That is something we've been trying to understand better, is what are the right representations for objects, and probably a point cloud representation is not the one that we need for manipulation. But there are problems where you would want to have a full sort of geometric understanding if you needed to do very accurate part sorting or part fitting or kitting or something like this, where this does feel like the pose of a known CAD model does feel like a reasonable representation. But when I'm buttoning my shirt or something, it's probably not the right representation. So that is a topic that we will cover, but mostly cover the ideas that people are working on, because it's a wide open issue. Very good. Thank you, everybody. I'll see you on Tuesday.